stream. I don't see a start stream.
Then it should be live, no?
Yeah, I think so too, but I don't see us live. Am I missing something very obvious? Okay, now we're live, I think.
I tried joining from my phone.
Okay, we're live. Now we're live. Okay, cool. Then I'm
Sure.
going to introduce you again. Yes, very quickly. This is the sixth meeting of PNS FPGA-based exploration of DRAM and RowHammer. And today we have a research paper talk by Giray Yaglikci. He's going to talk about a recent work of our group. And with that, Giray, I leave the live stream to you.
Okay. Thank you, Ataberk, for the introduction. And thanks everyone for joining. So today we will talk about understanding RowHammer under reduced wordline voltage. If you're not familiar with some words in this title, don't worry about it. I will give the proper background in a little bit. So this paper is a product of a collaboration between our group, Safari in ETH Zürich, and Galicia Supercomputing Center. And this was published in DSN conference, Dependable Systems and Networks, in 2022. Okay, so I guess you have seen this kind of PCB boards around. If you didn't see, so this is a DRAM module. This is used as the main memory in many systems today, and it has multiple chips on it. As you can see, each black box here is a chip. And within each chip, we have a hierarchical organization of these DRAM chips. So each chip has multiple DRAM banks, and each bank has multiple subarrays. And within each DRAM subarray, we have DRAM cells, each of which contain 1 bit of data, and they are organized as a 2-dimensional array. And we access them internally in a DRAM row granularity. And to activate a DRAM row, we assert the word line here, these blue lines. And once we assert the word line and activate a DRAM row or open a DRAM row, we use the bit lines to connect these DRAM cells to this structure called row buffer so that we can perform the reads and writes operations from this row buffer. Okay, let's look into the DRAM cell a little bit. So within each DRAM cell, we have a capacitor and an access transistor. So this access transistor is enabled by the word line, as I said, and when it is enabled, the capacitor is connected to the bit line. We usually drive this circuit with 1.2 volts. This is a number from DDR4. Of course, it can change from protocol to protocol or standard to standard. So this is a typical number, 1.2 volts you put on the capacitor, and if you have 1.2 volts here, it means either logic 1 or 0. If you have ground, it means the other way around. Okay, and there are several charge leakage paths here around the capacitor, around the access transistor. So this is a volatile type of memory. Once you put the data here, it has a limited data retention time, and after some time it will lose the data. So to avoid that, we perform these refresh operations that restore the capacitor voltage with a time period called refresh window. Okay, so when we want to access a piece of data, we should first find which row contains that data, and we need to open that row. This is a process that we call row activation. So it essentially fetches the row's content into the row buffer. And then when we want to do this row activation, we basically assert this word line, meaning we put some high voltage on this word line. And based on DDR4 standards, again, a typical value that you put on word line is around 2.5 volts. So this is significantly larger than what you put on the capacitor. And it allows you, if you're familiar with the transistors, how transistors work, it allows you some significantly large voltage difference between the gate and the source, so that you can turn on your transistor, enable your transistor basically, and then make it conduct the capacitor to bit line. So once you perform the row activation, your data is fetched into the row buffer, and you perform your column accesses, reads and writes from the row buffer. And then once you're done with a row, and you need to access data from another row, you first need to pre-charge. Pre-charge meaning that you close that row, and then you pre-charge the bit line voltage to some certain value, so that you can perform the next row activation reliably. I assume you're familiar with the RowHammer vulnerability, but this is a little bit of background again. So as I said earlier, we want to open rows to be able to access data within them. So when you open a row, you put a high voltage on the word line, and then once you close, you put the low voltage. So when you do this voltage swing a lot on the word line, high, low, you see bit flips in the physically adjacent rows. And if you keep doing that, basically you can have more bit flips in more rows. And here we call this row that we keep opening and closing the aggressor row, and the other rows, the affected rows, are as victim rows. So let's see how this happens from another aspect in a closer look. So here we have a DRAM cell from each row, like each of these 5 rows from the previous cartoon. And let's say this is our aggressor row. So we switch the voltage on the word line from low voltage to high voltage. So it creates some disturbance around, and the disturbance is stronger in close proximity, and it fades out as you go farther. Okay, so you can see over time how the word line voltage changes. So you put high voltage, you open the row, and then you close it, and then the word line voltage goes low, and then you open it again, you close it, you open it again, you close it, and then you see bit flips. And a major contributor of this disturbance is the voltage swing on this word line. So repeatedly toggling the word line voltage is a key to induce RowHammer bit flips. And with that, I will go to the executive summary. I just wanted to mention these in advance because they will be relevant in a little bit. So our motivation for this work is that repeatedly toggling the DRAM row's word line voltage causes bit flips in nearby rows. And this vulnerability, called RowHammer, worsens in denser DRAM chips, so it's an important problem to tackle. And understanding RowHammer enables designing effective and efficient solutions. But the problem is that no study before this work demonstrates how word line voltage affects RowHammer. So we know that toggling the word line voltage has a huge impact on RowHammer, but we don't know how the magnitude of this voltage toggling affects. So our goal is to experimentally understand and show how VPP, or word line voltage, affects RowHammer and DRAM operation. And to this end, we perform an experimental study on 272 DRAM chips from 3 major DRAM manufacturers. And we come up with 6 observations showing that with reduced VPP, bit error rate caused by a RowHammer attack reduces significantly. And a row needs to be activated slightly more times to induce the first bit flip. So it means that when we reduce voltage, we can reduce RowHammer vulnerability, right? But it also has some effects on the DRAM operation. So we also come up with 9 observations showing that with reduced VPP, most of the DRAM chips still reliably operate because of when we use the nominal timing parameters, and this is because of the large guard bands that the DRAM manufacturers already put there. And when we look at the erroneous DRAM chips, the small fraction of erroneous DRAM chips, we find out that they can still reliably operate with a longer row activation latency. So if we increase the latency a little bit, they reliably work again. And also, if we enable some singular correcting codes or if we double the refresh rate for a small fraction of DRAM rows, we can make them reliably work. Okay, in conclusion, reducing wordline voltage can reduce RowHammer vulnerability without significantly affecting reliable DRAM operation. Okay, let's move to our motivation. So RowHammer is an important problem. And when we look at the minimum activation count to observe a bit flip, it got reduced more than an order of magnitude in less than a decade. And with some projection, we know that the defenses are becoming prohibitively expensive. Excuse me. And we need a deeper understanding to address this problem. And the prior works investigate how RowHammer change across different DRAM standards and different manufacturing technology nodes. And also they explore how it changes with temperature, aggressor rows active time, and victim DRAM cells physical location. However, no rigorous experimental studies demonstrate how the magnitude of wordline voltage affects RowHammer vulnerability of real DRAM chips. In this work, our hypothesis is that reducing wordline voltage can reduce RowHammer vulnerability without significantly affecting reliable DRAM operation. And we will just test this hypothesis throughout all our experiments. And our goal is to understand how the wordline voltage affects RowHammer vulnerability and reliable DRAM operation on real DRAM chips. So let's move to experimental methodology. So we are using DRAM bander. Over here it's written softMC because this is an early version of DRAM bander, and this paper was published before DRAM bander. But this is a quite similar version to what you have in your hands, actually. So this is also the same board that you've been using. Many of you are using, I think. This is a Xilinx Vertex UltraScale board that has some DDR4 DIMM slots. So we plug in DDR4 DIMM here. This is our DRAM module. And we also clamp it with some heater pads from both sides. And there's a sensor here that is connected to the temperature controller, so we can keep the temperature stable. And we also have a power supply here that we provide the voltage to VPP externally from this power supply. So this setup overall gives us fine-grained control over DRAM commands, timing parameters, temperature, and the wordline voltage. And to characterize our DRAM chips at the worst-case conditions, first we prevent sources of interference during the core test loop. To do that, we disable DRAM refresh so that we do not refresh the victim row and fix or correct some bit flips, or avoid some bit flips. So we can observe the bit flips in circuit level. And we disable DRAM calibration events as well, so that we have like minimal variation in our in the timing of our DRAM commands. And we disable all sorts of RowHammer mitigation mechanisms so that they don't correct the bit flips or they don't refresh victim rows before we see bit flips. And we make sure that all our tests fit into a time window which is smaller than the actual refresh window, so that we do not observe any data retention bit flips. And we repeat our tests for 10 times so that we will have some stable data. And we also use the worst case access sequence, which is basically attacking a victim row from both sides and repeatedly accessing the two physically adjacent rows as fast as possible. Okay, so this is a summary table of the DRAM chips that we have used in this work. So we use chips 272 DDR4 DRAM chips from 3 major manufacturers, and these chips implement different densities, die revisions, chip organizations, and they're from different manufacturing dates, varying from 2019 to 2017 to Oh, okay, from 2016 to 2021. Okay, so if you check the extended version of this paper on arXiv, you can find more details about how we perform these experiments, meaning like these algorithms, and also more detailed information about every single DRAM module that we test. Okay, let's look at how RowHammer changes under reduced wordline voltage. So this is our high-level takeaway. When we reduce wordline voltage, we observe that we can reduce RowHammer vulnerability such that the number of bit flips that we observe is significantly smaller, and the activation count that is needed to induce the first bit flip increases significantly as well. So this is a plot where we have the wordline voltage on the x-axis. Remember that 2.5 volt is the nominal voltage, and then we will from right to left, we will reduce the wordline voltage, and we will check how the bit error rate changes. Bit error rate meaning how many DRAM cells experience a bit flip when we do the attack. And obviously, lower is better for this value, right? So different colors here identify different DRAM modules from this manufacturer B. And we observe that, okay, so these shades also show you how the behavior varies across different DRAM rows within the DRAM chip. And we observe that there is a general trend that is decreasing. So bit error rate reduces as wordline voltage reduces. So fewer DRAM cells experience RowHammer bit flips under reduced wordline voltage. And if you pay attention to this top, there are some data points here that are above 1.0. So we also observe that bit error rate increases for some modules, some rows. So reducing wordline voltage can cause more DRAM cells to experience bit flips, but this happens only in a small fraction of DRAM rows. And when we repeat this analysis for DRAM modules that are from 3 major manufacturers, A, B, and C, Micron, Samsung, and Hynix, we observe that the same observations are true for all of them. Okay, so here we again reduce the wordline voltage from right to left. And now this time we check the minimum activation count to induce the first bit flip. So if this value is higher, it means that an attacker should try harder to induce a bit flip, right? So here again, different colors identify different DRAM modules, and the shades are showing the variation across DRAM rows. And as a general trend, we see that the minimum activation count to induce the first bit flip increases as wordline voltage reduces. So we need more activations to induce a RowHammer bit flip. And again, if you focus on this part below 1.0, we observe that the minimum activation count to induce the first bit flip reduces for some rows, and the small fraction is around like 14% of this DRAM rows. And we again observe the same behavior across all 3 manufacturers. We have more analysis in the paper on that. So we look at wordline voltage's effect on RowHammer vulnerability, and we show that it varies across different DRAM rows and DRAM manufacturers. So we have the observation that the change in bit error rate varies across different DRAM rows and manufacturers, and the change in the activation count, so this is RowHammer threshold, varies across different DRAM rows and manufacturers again. And you can see more analysis, more in-depth analysis in the full paper or in the extended version on arXiv. Okay, so this was our first takeaway that says reducing wordline voltage reduces RowHammer vulnerability, right? So far it's good. When we reduce wordline voltage, the RowHammer vulnerability gets reduced, our chip is a bit more reliable, and everything is good, right? But that high wordline voltage is used for some purpose, and reducing it can hurt the other operations in DRAM chip, right? So in in the second part of this paper, we analyze that. So we question if it is really like without significantly affecting reliable DRAM operation. And the reason that we are suspecting this is because when you have a larger wordline voltage, you have a stronger channel here. And if you reduce the wordline voltage, then the channel strength, so your channel in the transistor gets weaker, so it conducts less, and then it can cause DRAM to work slower, and I will explain in a little bit. So in this part of the analysis, we also have two key takeaways. The first one is that most of the DRAM chips reliably operate using nominal timing parameters due to the built-in safety margins, or as known as guard bands. And the small fraction of these DRAM chips that exhibit some erroneous behavior can still reliably operate if you increase the access latency a little bit more. The other takeaway is that, again, most of the tested chips reliably operate using the nominal refresh rate due to the built-in safety margins, again, guard bands. And for the small fraction of DRAM chips that cannot retain data for the nominal refresh rate, you can use some singular correcting code or double the refresh rate only for a small fraction of DRAM rows, around like 16% of DRAM rows, and you can make them reliably operate again. Okay, let's dive into this second takeaway first. Here we look at the wordline voltage again on the x-axis. It goes from right to left, and we look at the row activation latency. So we activate the row, and we need to wait some certain amount of time until we perform the first column access, which is like, for example, a read, right? And we check how this value changes across different voltage levels. And each line here again shows the data from a different DRAM module. And again, we show the variations with shades. Excuse me. And we observe that the row activation latency increases as wordline voltage reduces. And this is an artifact of making the channels weaker. And this happens, but when we look at the nominal activation latency that is dictated by the specifications, we observe that this nominal latency is already quite large, actually. If you look at the value you observe at 2.5 volt, it's significantly smaller. It's around like 10 nanoseconds, while the nominal activation latency is around like 13.5 nanoseconds. So you already have this guard band. And despite this increase, we observe that in many rows, there is no problem. So 208 out of 272 DRAM chips complete row activation before the nominal activation latency. And this is true for all modules from all DRAM manufacturers that we test. And we observe that only 48 DRAM chips from manufacturer A reliably work with a row activation latency of 24 nanoseconds. So this is for, okay, I should go again here. So if you look at the values here above the nominal activation latency, for manufacturer C, for example, we do not need to change anything, right? So we can just use the nominal activation latency, and the activation event itself happens before this timing parameter is satisfied, right? So there is no need for any change here. But for chips from manufacturer A and manufacturer B, some chips require an increase in the nominal TRCD, or the row activation latency value. So we have 48 DRAM chips from manufacturer A that reliably work with a row activation latency of 24 nanoseconds around here. So if you increase the 24 nanoseconds from 13.5, they work. And from manufacturer B, 16 DRAM chips can work at the row activation latency of 15 nanoseconds. This is relatively a smaller change. And all DRAM chips from manufacturers see reliable work. Okay. So to show in a closer look how this trade-off happens, we wanted to provide some insights into Wordline voltage effect on DRAM operation. And for that, we conducted some SPICE simulation. And we use a 22 nanometer transistor model in the simulation. And we use these parameters that are written here. And this is a schematic of the circuits that we simulate. And we perform a Monte Carlo analysis with 5% variation. And we perform like 10,000 iterations. And we get this result. So what do we have here? So this is a simulation of how the bitline voltage changes over time when you perform a row activation. So since VDD is 1.2 volts, in the very beginning, we have the bitline voltage at 0.6 volts, which is the half of the VDD. So it's in the middle of the VDD and the ground, right? And once we activate, we observe that the bitline voltage increases following this kind of curves. And these curves, like different colors here, mean different voltage levels. And once the voltage reaches a threshold value called V threshold, row activation is completed, so you can read the data reliably at this point. But this point, if you look at like when each curve cuts this point, you can see like it happens in different times on the x-axis. So this cut point shifts from left to right as bitline voltage, Wordline voltage reduces from 2.5 volts to 1.7 volts. So the takeaway is that bitline voltage takes longer to reach VTH when we reduce the Wordline voltage. And this is because of this access transistor has a weaker channel when we reduce the Wordline voltage. And row activation latency increases with reduced Wordline voltage. And when we look at the variation in row activation latency, we observe that at 2.5 volts, the variation is exhibited, is shown with this like yellow curve here, right? So we have a peak around like 11.5 nanoseconds, and the tail goes to 0 around like 13 nanoseconds on the right hand, right? So this means that if we use this 13.5 nanosecond, for example, this dashed line here, for 2.5 volts, we are safe because we can, this is a latency parameter that is larger than the actual latency of every single row in the simulation. And the nominal row activation latency is around like 13.5 nanoseconds, and the worst case TRCD mean is here when VPP is around like 1.9 volts based on our simulation. So as a disclaimer, I have to say that this is not showing the picture for the real DRAM chips, because while performing these simulations, we did not, and we still do not have the actual circuit design parameters and actual modeling of the manufacturing process variation of the real DRAM chips. So we are just doing our best effort to mimic their behavior using the Monte Carlo simulation and sweeping some parameters. And we observe that this distribution actually shifts right when we reduce the Wordline voltage. So when we reduce from 2.5 volts to 1.9 volts, the worst case row activation latency is still lower than nominal value. And the guard band reduces from 4.4% to 1.5%. So we sacrifice some guard band, but we still can work reliably. Okay. And the SPICE simulation results agree with our observations based on experiments on real DRAM chips. And yeah, so this is our disclaimer. It's not identical, but if you look at the trend, they show the same trend. Okay. So we also looked into in the paper how wordline voltage affects the DRAM charge restoration process. We show that the DRAM cell capacitor voltage can saturate at a lower voltage than the nominal voltage that it would saturate with the nominal wordline voltage when we reduce the wordline voltage. Okay, and the DRAM cell's charge restoration latency can increase with reduced wordline voltage as well. And you can see all these analyses in the full paper. Okay, so based on that, we also continue real DRAM chip characterization study for the charge restoration and retention time. So there is no way that you can measure charge restoration, unfortunately, with the real DRAM chips, because it's something really internal and you cannot practically put a probe on some capacitor's cell voltage, sorry, a cell's capacitor voltage. But what we can do is we can infer what's going on by looking at the data retention time, because when you have a poor charge restoration, you would have a poor data retention time. So this is what we do here. So we look at how the data retention characteristics change, and we observe that most of the DRAM chips can still reliably operate using nominal refresh rate, but some of them require some mitigation mechanisms that I will show in a little bit. So here, what we do is, on the x-axis this time, we increase the refresh window from 64 milliseconds to 16 seconds. And we look at the how data retention bit error rate changes when we do this. So as you can see, all the curves are following an increasing trend here. It's an exponential increase, if you will. And each color corresponds to another wordline voltage level. Okay, and yeah, we see that data retention bit error rate increases as wordline voltage reduces, and more DRAM cells tend to experience data retention bit flips when wordline voltage is reduced. And when we check, 216 out of 272 DRAM chips reliably operate using nominal refresh rate, which is 64 milliseconds. So they have the, excuse me, they have a data retention bit error rate of 0. And when we look at, when we repeat this analysis for all DRAM modules from all manufacturers, we observe that our observations are true for all of them. Okay, so we also look at the special distribution of data retention bit flips, and we observe that there are no 64-bit long data verse that has more than one bit flip. So what this means is that you can just perform a singular error correcting code mechanism on these, and once you have a data retention bit flip, it will not be like more than one bit flip in a 64-bit word, and you can correct that error when it happens. So you can still reliably operate at the nominal refresh rate. You will have errors once in a while, but this ECC or error correcting codes will correct them. Here's another plot where we have on the x-axis the number of 64-bit data verse with 1-bit flip, and on the y-axis we have the fraction of DRAM rows. So we are looking at how these bit flips are, or erroneous data verse, are distributed across different DRAM rows, right? And we observe that a small fraction of DRAM rows contain erroneous data verse. And when we repeat this analysis for 64 millisecond refresh window and 128 millisecond refresh window, we observe that it's still true. Only a small fraction of DRAM rows have erroneous words at the smallest refresh rate. So it means that in many rows, even at 128 millisecond refresh window, you don't observe any bit flips. So this means that for this small fraction of DRAM rows, around 16% or 5% in this case, What you can do is you can just double the refresh rate or quadruple the refresh rate in 120 millisecond case, and you will be fine basically without any errors. Okay, to conclude, we provide the first RowHammer characterization under reduced Wordline voltage, and experimental result. We provide some experimental results out of 272 real DRAM chips, showing that reducing Wordline voltage reduces RowHammer vulnerability, meaning that it reduces the number of DRAM cells that experience RowHammer bit flips, and also it increases the number of activations you need to induce the first bit flip. So it makes a RowHammer attack to be performed harder. And at the same time, reducing Wordline voltage increases the row activation latency. So more than 76% of the tested DRAM chips reliably operate using nominal timing parameters, even though the activation latency is in fact increased. And the remaining 24% can still reliably operate if you increase the row activation latency. And this reducing Wordline voltage also reduces the data retention time due to a relatively poor charge restoration process. And even though this is the case, we observe that for 80% of the DRAM chips, they reliably operate using nominal refresh rate, and the remaining 20% can reliably operate if you implement some single error correcting codes or double the refresh rate for a small fraction of DRAM rows. And yeah, as a result, we conclude that reducing Wordline voltage can reduce RowHammer vulnerability without significant effect on reliable DRAM operation. And that's the end of my talk, and I'm happy to get any questions that you might have. Or maybe YouTube has.
So I don't see anything on YouTube. Thanks, Giray, for presenting. Does anyone in the Zoom audience have questions for Giray? No?
Okay, then I hope this is a good example of like how DRAM Bender can be used for testing different vulnerabilities or different effects in DRAM chips. Yeah, I hope you find it as a good example.
Yeah, thanks for the nice remark, Giray. With that, I'll stop our live stream.